Okay, here's a couple of problems we're going to show how to work that are based on the Chemistry 120 Joy of Chemistry class, but these are also used in other chemistry courses as well. The first question here, we are going to calculate the mass of 2.50 times 10 to the fourth molecules of nitrogen gas. So the first thing I think that you want to do is write down what's given, 2.50 times 10 to the fourth. And here's the tricky part, I think. It says molecules of nitrogen gas. So remember, molecules, nitrogen occurs as N2, and so it's not just one nitrogen, it's two. And the reason why we know that is because it says molecules here. All right. So in order to do this problem, we know two things. First of all, we can't go directly from molecules to mass, but we can go from molecules to moles to grams. So, and you're going to have to forgive me a little bit on my writing here. What's happening is I'm not using my tablet PC today. I'm using just a tablet. And the tablet, when you're writing, it's writing blind. You can't see what you're actually writing until you look up at the screen. So it's going to look a little sloppier today. The advantage of the tablet is that I can do this on a desktop instead of using the tablet PC. So this will get better as we go along, but this is going to be a little bit of a practice run here. All right, so what we know that we know that in order, so we see that there's two conversion factors. There's going to be one here, and there's going to be one here. So in order to go from molecules to moles, we have to know how much 1 mole is, and we know that 1 mole is equal to Avogadro's number. All right. So in this case, 1 mole of nitrogen molecules equals Avogadro's number of nitrogen molecules. And then the other relationship we're going to need to know is the molar mass of nitrogen. And again, this is I think the tricky part, because if you don't look at that carefully and go, oh yeah, nitrogen naturally occurs as a diatomic substance, then it's going to be hard to solve this problem. So we know that 1 mole of nitrogen gas equals, if we go to the periodic table, nitrogen weighs 14.0 grams per mole. So diatomic nitrogen is going to be 28.0 grams. That's how much 1 mole of nitrogen is going to weigh. So we're ready to solve the problem. So to solve the problem, start with what's given. This has three significant figures, 2.50 times 10 to the fourth molecules of nitrogen. Now that's a lot less than Avogadro's number, so we know we're going to get a really small number here. Multiplication sign, quotient bar. We want to get rid of the molecules of nitrogen, so we're going to use Avogadro's number here. Molecules of nitrogen is 1 mole of nitrogen. Extend that out. All right, and we know we set this up right because the molecules of nitrogen are going to cancel out, and that's going to give us moles. And then the next step is we need to get rid of the moles and end up with grams. So moles of nitrogen, 1 mole of nitrogen weighs 28. Let's finish it out. 28.0 grams. All right. So let's get the calculator and take 2.54 exponential to the fourth. I mean 2.50 exponential to the fourth, and divide that by Avogadro's number, 6.022 exponential 23, and then multiply that by 28. And we get 1.16, We get for an answer 1.16 times 10 to the negative 18 grams. And it really should be a small number because, again, this is so far away from Avogadro's number. So we expect this to be a really, really small number. And the three significant figures, if we go back up here and look at this, this has three significant figures. This has four significant figures, or that's how many I carried. Oops, that's how many I carried here. And let's close that out. And then three significant figures in 28.0, so we should have three here. So there's my answer to three significant figures. All right. So again, the plan of action is to write down what's given, and then think about how you're going to get from what's given to what you're trying to find. And again, there's no direct relationship between molecules and moles. Remember, molecules is number of particles. Moles is a grouping of those number of particles, just like a dozen groups 12. And then the key is that every element on the periodic table has a different mass. So we have to figure out the molar mass of that substance, in this case the nitrogen molecules. That's actually down here. We have to figure out the moles of nitrogen and how much that weighs. All right, so this part again from the periodic table, and that's a key component of solving the problem. All right, let's move on to the next problem. All right, number 2 here, carbon dioxide emissions in China declined by 9% over a 5-year period ending in 2000. If there was 5 times 10 to the 8th metric tons of carbon dioxide was emitted in 1995, how much carbon dioxide was released today? Now, I think most of you can do this problem. This is just like a problem like you go to the store and you see a shirt that's $20 and it's marked 20% off. And so you figure out that the shirt's going to cost $16. 20% in decimal form is 0.20 times the $20 is going to give you 4.0 or $4 off. So you subtract that from the original amount, $20, and that's how you know it's $16 for the shirt. Well, this works the same way. You write down what's given. It's 5. Oops, we had a problem here. Let me go back. I hope you'll bear with me on this with this tablet, because it's going to have some advantages in the long run over the tablet PC. All right, so let's write down what's given. 5.00 times 10 to the 8th metric tons. We'll just say MT here, okay, of carbon dioxide. All right, and that's what was in 1995. So let's put a little 1995 here. And we know that in 2000 that we have 9% less. 9% less. All right. So here it is. This is like the cost of your shirt. You're going to multiply that by the percent that the shirt was off, 20%. In this case, it's 9% off, right? 9%. So the way you would do this, to make sure you do this correctly, some of you do it in your head, but just the easy way is just to say 9 divided by 100. All right? That's what 9% is. That's the whole thing with percentages. The reason why we like this is because that little symbol there represents 9 over 100. So let's multiply this out. Let's take 5 exponential 8, 5 exponential 8, and then multiply that by 9 divided by 100, and we get 4.5 times 10 to the 7th. 4.5 times 10 to the 7th. All right, so let's write that down here. 4.50, we could carry that out if we wanted to, 0 times 10 to the 7th metric tons. All right. So now that's how much we lost. So if we take the 5.00 and we multiply that by 10 to the 8th, all right, that's how much we had emitted in 1995. And we're going to subtract from this. Now, watch this. You can do it on your calculator, but I just want to show something here. This is important to know about significant figures and what we're doing here. If I want to subtract this number from 5 times 10 to the 8th, if I want to do this without the calculator, I got to get these exponents to agree. So if I want to convert 4.50 times 10 to the 7th to some number times 10 to the 8th, watch what happens here. This becomes 0.450 times 10 to the 8th. Now you're going, how'd you get that? Well, you know 10 to the 8th is a larger number than 10 to the 7th. So we know that 4.50 times 10 to the 7th is smaller than 1 times 10 to the 8th. Let's think of it that way. So if I move the decimal one place over and make this number less than 1, then I can raise this power up to the 8th. So you say, why did you do that? Well, when we go to subtract here, it's going to be 0.450. And when you do addition and subtraction, you generally want to have the same exponents so you can see where the significant figures are. So we're going to take this number, 0.450 times 10 to the 8th, and we're going to subtract that from 5 exponential 8, and we get 0.455 or 4.55 times 10 to the 8th. All right, so this is our final answer, 4.55 times 10 to the 8th. So this is how much carbon dioxide was released in 2000. And the significant figures, this number was known to the hundreds place, 5.00 times 10 to the 8th. This number, because of the multiplication, was actually known to the thousands place, 0.450. But the weakest link here is this place, the hundreds. So we can only report our final answer to the hundreds. So 4.55 times 10 to the 8th. So we do see a reduction. This is what we had in 1995. And this is what we had in 2000. And that's a 9% reduction. And that 9% is what we calculated right here. And this is how we calculated it up here. Again, it is no different than buying a shirt. It's like this was your $20 shirt. It's 20% off, so it's multiplied by 20 divided by 100. So when you multiply that 20 divided by 100 times $20, you're going to get $4 here. You subtract the $4 from the original price of the shirt, and that tells you that your shirt's $16, and then you got to add the taxes. But that's the same principle here. It's declined by 9%. That's your reduction. This is the original amount in 1995, and we're trying to figure out what the amount is in 2000. I hope this helps. This problem's really testing you on your percentages again. Remember, we had percentages, which is like parts per hundred. Then we have parts per thousand, parts per million, parts per billion. And that's kind of what this problem's kind of bringing back that from chapter 1.